Hello all. So our last type of related rates problem is going to do with area and volume. Again, we've got just a small problem set here, 4 problems for us to practice on because they do take a little bit longer. Let's get out our notes and we're going to get started. So the key for all of the area and volume ones is to find the formula. That's going to give you the equation that you're going to take the derivative of. So in number 1, it says the area of a square is decreasing by 1 meter squared per minute. So again, we've got a rate here in terms of time. That's going to be our sign that it's a related rates problem. So how fast is the side of the square shrinking when the side is 30 centimeters? So when it says find the formula, we know we have area of a square. So in this case, hopefully this one you don't have to look up. If we have a square, the area is s squared. Some of these equations you'll have to look up. Feel free to Google, look in your planner, whatever makes the most sense. So the formula that we're going to be taking the derivative of, our equation, is area is equal to s squared. Given this equation, we know that dA dt, the rate of the area, is decreasing by 1 meter squared per minute. So that's -1 because it's decreasing meter squared per minute. We know that S is equal to 30 and we want to find ds dt. We want to know how fast the square is shrinking. Now, since this isn't obviously simplifiable, I'm just going to do the derivative in terms of t on both sides. So that becomes 1 times dA dt is equal to 2s times ds dt. Remember, ds dt is what we want, so we're going to plug in for everything else. This becomes -1 is equal to 2 times s, which is 30. That then would equal, whoop, I've made a common mistake. So what we're going to end up with is that the rate of the side is shrinking by 1/60th ds dt. But if you put this down, you would not be correct, and this is why it's really important to think about units. So what this is it's -1 meters squared per minute for the -1 divided by 60 is measuring side length, so it's 60 centimeters. So what we are going to have to deal with is the fact that we have meters for one of our units and centimeters for the other. So what I'm going to do then is I am going to convert, moving the decimal place 2 spaces to leave you just a meter, and then I end up with -1 meters squared over minute divided by 0.6 meters. The meter squared and the meter will cancel out with the division, and this will then make sense in terms of what the actual value is, what an actual unit would be, which would be -1 over 0.6 meters per minute. Meters per minute would be the logical change of the side length, as the area is being changed in meters squared per minute. I'm going to turn this into an acceptable fraction by moving the decimal place 2 spaces, leaving me with -10 over 6, which simplifies to -5/3 meters per minute. There you go. Now, there might be some ones with volume which are slightly more complicated formulas. So number 2, air is being pumped into a spherical balloon, so the volume increases by 10 centimeters cubed per second. All right, there's our rate. So we know it's a related rates problem. We know that the rate of the volume is 100 centimeters cubed per second. How fast is the radius increasing? So we want to find the rate of the radius in terms of t. This is what we want. And then our volume is 192 pi centimeters squared. In this case, our units are not going to get weird on us, so that's awesome. And now we just have to find the formula. Now, as I said, some of these formulas you definitely will have memorized. I do not expect you to have the volume of a sphere memorized. Feel free to go look it up however you need to. In this case, the volume of the sphere, I will tell you, is 4/3 pi r cubed. So the first thing we're going to do is start with that formula. It doesn't have an obvious way to simplify it, so I am going to start by taking the derivative in terms of t of that volume formula. So V is equal to 4/3 pi r cubed. Now, one thing that's important to note about pi is like it's a letter, but it's still a constant. So here we have 1 times dv dt. 4/3 pi is the coefficient, so that just stays out in front. R cubed, the derivative would be 3r squared using the power rule, and then dr dt, like so. So in this case, we know dv dt, we know that this left side is going to be 100. We can simplify a little bit on the right side, 4/3 and then times 3 right here. The 3 and here cancel out, leaving us with 4 pi r squared times dr dt. So, oh no, just like we ran into in our last video, we're going to end up needing to find r, and that's where we're going to look at this other piece of information we're given. It says that the volume is 192 pi centimeters squared. I'm going to use the space on the left here to find r. So using that same formula, we know that 192 pi is equal to 4/3 pi r cubed. I'm going to divide both sides by pi really quick just to make that nice and straightforward. Then what I would do is multiply by 3 and divide by 4. So 3/4 times 192 is equal to r cubed. You can get a calculator or do a little bit of long mathematics. 144 r cubed. It'd be really lovely if it was an r squared and we could just say 12, but it's not. So I'm going to plug into my calculator to the power of 1/3. Right? So in my calculator, most of you won't have a cube root button. So if you want to do this on your calculator, power of 1/3. So r is equal to approximately 5.241. I'm not going to round, I'm just going to keep using my calculator when I plug that in. So I end up with 100 is equal to 4 pi times 5.241 cubed dr dt. When I do the division there, I can multiply together, divide the 100. I end up with dr dt, the rate of the radius, as 0.290, and the unit would be centimeters per second for time. Hopefully this related rates, stretching it out over this time frame, makes it feel very approachable. It's, as I said, it's implicit differentiation, just where you're always using a different variable. If you get stuck on anything, please make sure you're getting in touch, especially before your test next